Hello everyone. In this, we will understand about manufacturing inventory model with the shortages. So in this model, an item is produced and consumed simultaneously for a portion T1 of the total cycle time T. Means T1 is a part of the total cycle time T. Another portion T2 of the cycle time, what we do is we only consume the item. And in this model, the cost of production per unit is assumed to be the same irrespective of the production lot size. And even we consider the demand to be uniform throughout the year. Stockout is permitted in this model for a period T3, and it is assumed that the stockout units, whatever is the quantity, that will be produced during a period T4 with some penalty. And this is called as back ordering. And what are the notations being used in this model? Here we use capital D for annual demand, which is nothing but the number of units required per a year. And K, small k, is the production rate, which is number of units produced per year. Most of the terminologies or notations are the same, what we had seen in the earlier manufacturing model without shortages. Except that here the addition thing will be C suffix S, which is shortage cost per unit per annum. And CO is considered to be the setup cost per setup. CC will be the inventory carrying cost per unit per annum. And capital P is the cost of production per unit. And small t1 is the period of production as well as consumption of the item, satisfying the period's requirement. T2 will be the period of consumption only. T3 will be the period of shortage. And T4 will be the period of production as well as consumption of the item satisfying back order. Now our small t, which is the total cycle time, is all the sum of these four, means T1 plus T2 plus T3 plus T4. I suffix m is the maximum inventory and S suffix m is the maximum shortage or maximum stockout. So based on this, we will understand the graphical representation of this model. Here we have the y-axis, y-axis, and this is our x-axis. And this is our origin. And initially, what we do is we consider the time period T1. This is our time period T1. Let me split this into two parts. This is our time period T1. This is our time period T2. This is our time period. Sorry, I should split that also. So this is our T3, this is our T4, means this portion is T3, this portion is T4. Means during this T1, period T1, we manufacture as well as consume, means we manufacture at the rate of K units, that is the production rate is K units, sorry, K is the production rate, means number of units produced per annum. So we consume at that particular, we produce at that rate and we consume at the rate D. So that means this overall the rate will be K minus of T. In this portion of time, that is T2, we only consume at the rate of D. And here this gets continued. And here it will be K minus D. This is also K minus D and this is D. So that is the way the model is represented. Now, from this we can able to say that our this is considered to be the, this point is considered to be the maximum inventory. Means this portion is your IM and this portion is your stock maximum shortage. This is SM. So this is your SM, the gap between that. Okay, so now based on this, we can very well say this IM is nothing but K minus D times T1. K minus D times T1. let us, in that case, we can say T1 as Im divided by K minus of D. Let us consider that as equation 1. And then we can also say Im in terms of D as D times T2. So Im can be represented as D times T2, which means our T2 will be Im divided by D. Let us consider that as equation 2. Same way, we can express this Sm in terms of T3 and T4 as Sm will be D times T3, which means our T3 will be Sm divided by D. Consider that as equation 3. Again, Sm can be represented in terms of T4 as Sm will be K minus D times T4, which means our T4 will be Sm divided by K minus of D. Consider that as equation 4. Now, if you compare this T1, T2, T3, T4, some of the elements are common. So if I try to merge this T1 plus T2, I will be landing up with 1, Im will be common, I will be landing up with 1 divided by K minus D divided plus 1 divided by D. Here also, if we club these two, I will have the same thing. That means let us calculate first what will be 1 by K minus D plus 1 by D. If we do that, the LCM is D times K minus of D, which means here we will have D plus K minus D. So here this D and D gets cancelled. We will get K divided by D times K minus D. If I bring that K to the denominator, we will have 1 divided by D times K minus D divided by K. Let us club this together. So we can divide individually. K by K will be 1 minus D by K. So this will become now 1 divided by D times 1 minus of D by K. Since this D and K do not involve Sm, Im, Q, we will consider this 1 minus D by K as some constant. So let us consider alpha equal to 1 divided by 1 minus of D by K. So if we consider that, then we can rewrite this 1 by K minus of D plus 1 by D as 1 by D alpha, D times alpha. So now another thing we can say is, if we consider if capital Q is the production lot size, that is what we are interested in finding out. What should be the production lot size? Suppose if we consider that as Q, then we can express this Q as, see, where all manufacturing is happening. Manufacturing is happening in time T1 and also in time T4, whereas in T2 and T3, only consumption is happening. Only during the period T1 and T4, manufacturing activity is happening. So, and that is going to be made at the production rate K. So we can say Q as T1 times K plus T4 times K, which can be written as K times T1 plus T4. So Q can be expressed as K times T1 plus T4. Now, what is T1 and what is T4? You may notice T1 is Im divided by K minus D. T4 is Sm divided by K minus D. Let us substitute that. We can say this as K times T1 is Im divided by K minus D. And T4 is Sm divided by K minus D. So now we can take out this k by d outside. So we will have k divided by k minus of d times im plus sm. Or we can rewrite, we can bring that k down. We will have 1 divided by k minus d by k times im plus sm. So again, if we divide individually k with this k, so you will have 1 minus d by k, 1 divided by 1 minus of d by k times im plus sm. Already we assumed this 1 minus d by k as alpha. Oh, I'm sorry. I should have written here as simply 1 minus of d by k. One minus of d by k, not 1 by 1 minus of d by k, because we considered this as this one is denominator. So we simply wrote alpha. So we can rewrite this as im plus sm divided by alpha. That means we can simply say im plus sm is q times of alpha, or we can rewrite im as q times alpha minus of sm, minus of sm. So that is one thing which is available. Now let us consider our t. We know t is t1 plus t2 plus t3 plus t4. And t1 is what? T1 is im divided by k minus d, and t2 is im divided by d. So we can say this is im times 1 by k minus d plus 1 by d. That is the first two terms. And similarly, this t3 plus t4 will be sm times, you may notice it is like similar like this. Sm is common, so we can write 1 by k minus d plus 1 by d. So sm times 1 by k minus d plus 1 by d, which can be written as, we already know this, 1 by k minus d plus 1 by d is 1 by d alpha. Yeah, 1 by alpha, d alpha. So we can say now this one as im times 1 im divided by d alpha plus sm divided by d alpha. Or we can rewrite t times d alpha as im plus sm. Im plus sm, we know it is q alpha, so I can equate this to, from here, we can equate it to q times alpha, and which means I can cancel both sides alpha, so we will have td equal to q, or t is q divided by t. So that is one expression we got. We have this expression and we have this expression. So now let us proceed with our cost function. we can say total cost per annum is setup cost per year plus carrying cost per year plus shortage cost per year without considering the total cost of the production or the product, since that is independent of the quantity. So we can say now TC will be TUC, setup cost plus carrying cost plus shortage cost. And your setup cost will be number of setups per annum into the setup costs per setup, then average inventory times CC plus average shortage times CS. Now, the number of setups will be number of setups per annum will be D divided by Q. Then the average inventory, we will see where all the inventory is available in the model. That is maximum inventory, that is IM. It is available in the period T1 and also available in the period T2. I mean this IM. So that means the area of this triangle for the entire period we have to calculate. Area of the triangle is the base, that is T1 plus T2 into height, which is IM. And this is for the whole period, in the sense for the whole period T, for whole cycle time T. So which means average inventory will be half times BH. Base is T1 plus T2 into the height, which is IM, for the entire period, entire cycle time T. Similarly, average shortage. Average shortage will be the area of the triangle which is formed wherever the shortage is existing. Shortage is in this portion. The height will be SM and the base will be T3 plus T4. And the total cycle time is T. So it is half times the base, which is T3 plus T4 into height, which is SM, divided by the total cycle time T. So that will become your average shortage. Now, let us consider this T1 plus T2. We already have T1 as here. T1 as IM by K minus D, T2 as IM by D. So IM is common. So you will have IM outside and then you will have 1 by K minus D divided by 1 by D, which we already have 1 by D alpha. So T1 plus T2 will be IM times 1 by K minus D plus 1 by D, which will become IM divided by D times alpha, because 1 by K minus D plus 1 by D will be, somewhere we wrote that. Yeah, here it is 1 by D alpha. So the D alpha will come in the denominator. Similarly, T3 plus T4 will be, we may go back and see what is T3 and T4. It is SM by D, SM by K minus D. That means SM is common. So we have 1 by K minus D plus 1 by D. So T3 plus T4 will be SM times 1 by K minus D plus 1 by D. So that we will get SM divided by D alpha. Therefore, the total cost will be number of setups, that is D by Q, times CO plus average inventory. One more thing we may notice, this average inventory, we can write this IM as like this. This means I'm converting into two variables instead of, I'm converting the IM in terms of Q and SM. So Q alpha minus SM. So let me rewrite this first. So average inventory is T1 plus T2 times IM divided by 2T. 2T times Cc plus average shortage. Average shortage is T3 plus T4. T3 plus T4 times Sm divided by 2T. So that this multiplied by CS, I mean shortage cost per year per annum. So therefore this TC will become now D by Q times CO plus, we already have T1 and T2, which is Im by D alpha. So this becomes Im into Cc divided by D alpha. So 2T D alpha. I wrote 2T also, what is there in the denominator, and then 2T I wrote, and then this D alpha also I wrote. Similarly, plus this is multiplied with the Cc plus T3 plus T4, which is Sm by D alpha. So Sm by 2T D alpha. Here again there is an Sm and then Cs. So this is nothing but D by Q times CO plus, I think I wrote it 2 times. Just a moment. Yeah. Only once the Cc will come. And then this is Im square Cc by 2 times Q, I'm sorry, T. T is in terms of D by Q, I think. Yeah, Q by D. So we can write that T as Q by D. Q divided by D multiplied by D times alpha plus Sm square Cs divided by 2 times T. T is nothing but Q by D into D alpha. So this D and D gets cancelled here. This D and D gets cancelled here. So again our TC will be D by Q times CO plus Im square. Here we converted this one. Im is nothing but Q alpha minus Sm. So instead of Im, I will replace it Q alpha minus Sm, the square times Cc divided by 2 times Q alpha. Here we'll retain Sm as Sm only, so Sm square Cs divided by 2 times Q alpha. So this is our total cost function. Now, in order to find the optimal Sm value, that is maximum shortage value, we will partially differentiate this function with respect to Sm as below, which means partial derivative of Tc with respect to Sm. First term do not involve any Sm, so it becomes 0. Second term, only the numerator has got Sm. Rest of the things we'll write it as a constant in the sense Cc by 2Q alpha. Then if we differentiate this Q alpha minus Sm the whole square, it becomes 2 times Q alpha minus Sm, and then differentiating this minus Sm with respect to Sm, we get minus 1. Plus, here everything else is considered to be constant except for this Sm square. If I differentiate Sm square, it is 2Sm. Rest of the things we'll write as it is, considering it as constant, is equal to 0. Now, when we cross multiply, this 2Q alpha gets cancelled, means it will be getting multiplied with 0. So I can straight cancel this. Then I can now write it as 2 times SMCS equal to, I'm going to take this entire thing to the other side. It becomes 2 times CC times Q alpha minus SM, because negative, if I take it to the right hand side, it becomes positive. Both sides we can cancel 2. So we will expand this now. SMCS is equal to Q alpha CC minus SMCC. Now bring this SMCC to the left hand side. We will have SMCS plus SMCC is equal to Q alpha CC. Means our SM can be taken common in the left hand side. So you get CS plus CC. Let me write it as CC. C is equal to Q times alpha CC, which means our optimal maximum shortage, that is SM, will be Q alpha CC divided by CS plus CC. So since this is optimal, I'll put a star over there. This is the optimal maximum shortage. Now again going back to this function, total cost function, let me rewrite it. TC is equal to, now we will be interested in finding out the optimal Q value. So I will take this Q to the numerator. So you get D Q inverse CO plus Q alpha minus SM the square times CC divided by 2Q alpha. I think I wrote it. Yeah, 2Q alpha minus SM the square CC divided by 2Q alpha. And this one also, as it is, we will take this Q to the numerator. So plus SM square CS Q inverse divided by 2 alpha. Now we will partially differentiate with respect to Q. We get partial derivative of total cost divided by with respect to Q. It will become now DCO is considered as a constant, and if I differentiate Q inverse, it is minus Q to the power of minus 2. Plus, here the constants are CC divided by 2 alpha. And then you will be left with this Q alpha minus SM the square divided by Q. It is like U by V. So we will differentiate, when we differentiate, it is U dV by dx. Sorry, du by dx means 2 times Q alpha minus SM. And if I differentiate Q alpha, it will be alpha minus Q. This Q alpha minus SM the square. Q alpha minus SM the square. And if I differentiate the denominator Q, it is simply 1. Whole thing divided by Q square. Next, the last one, that is plus. Except for Q, everything else to be considered as constant, which means SM square CS divided by 2 alpha. And if I differentiate Q inverse, it is minus Q to the power of minus 2. This is equated to 0. So we will retain this in the left hand side. This expression and this expression, since it has got negative values, we'll take it to the right hand side, which means what is that expression? CC by 2 alpha CC by 2 alpha times. Now in this we may notice Q alpha minus SM is common. So Q alpha minus Sm, sorry, minus Sm is constant. We are taking it outside. So here we will have 2Q alpha, 2Q alpha inside the brackets minus, we took Q alpha minus Sm one outside. So you will have Q alpha minus Sm one more inside. Q alpha minus Sm inside. Then we have this Q square in the denominator. Equal to, let us take this expression to the right hand side, it becomes positive. So I can write in the right hand side this one as dCO by Q square. dCO by Q square. Similarly, this one also will take it to the right hand side. We can rewrite it as Sm square Cs divided by 2 alpha Q square plus Sm square Cs divided by 2 alpha Q square. Because we equated it to 0, that's why we took these two terms to the right side. Now everywhere in the denominator Q square is there, we can cancel that, both left hand side and right hand side. Now just multiply it by 2, multiply both sides by 2, we get, if we do that, what will happen here, this 2 will go, you will only have Cc by alpha outside. Here Q alpha minus Sm, and then this one 2Q alpha minus Q alpha will become Q alpha, minus or minus Sm becomes plus Sm, is equal to, since we are multiplying by 2, you will have 2 dCO here, plus here 2 in the denominator will be knocked off with this 2, whatever we are multiplying. So you will simply have Sm square Cs by alpha. Now this left hand side, you may notice it is like A minus B into A plus B. So Cc by alpha. So we can write it as Q square alpha square minus Sm square is equal to 2dCO plus Sm square Cs by alpha. Let us expand this, what you call left hand side. We will have Cc Q square alpha square divided by alpha minus Cc Sm square divided by alpha is equal to 2dCO plus Sm square Cs by alpha. Now we will take this denominator alpha to the right hand side. It will go to the numerator. So we will have Cc Q square. Oh, sorry, here itself this gets cancelled. So I can write it as alpha. This we will take it to the right hand side. So you will have 2dCO plus Sm square Cs by alpha. Taking this through the right hand side, it becomes positive. So plus Sm square Cc by alpha. Right. So now what will be Q square then? Q square will be this Cc and alpha will go to the right hand side to the denominator. So we will have 1 by Cc alpha times 2dCO. Here we may notice Sm square by alpha is common plus Sm square by alpha times Cs plus Cc. Now we already evaluated optimal maximum shortage, which is Q alpha CC divided by CS plus CC. This means that SM square will be Q square alpha square CC square divided by CS plus CC the whole square. We will substitute this down in the sense Q square will be now let us individually multiply 2dCO by CC alpha plus SM square. Just now we saw it is Q square alpha square CC square divided by CC plus CS the whole square. There is an alpha in the denominator. We will write that also. And then here we have CC plus CS. So one term gets cancelled. In the denominator, you will have now CC plus CS. Now this term has got now Q square. We will take it to the right hand side. Now one more thing we can do is one alpha will go. So we will have Q square minus Q square I think this should be when I multiply here CC, I think I left this CC alpha should be there. So which means one more alpha gets cancelled. This gets cancelled and this will be simply CC. Means Q square minus Q square CC by CC plus CS. I mean, if I take this entire thing means Q square CC is there in the numerator. Denominator you have only CC plus CS that is being taken to the left hand side. This will be equal to 2dCO by CC times alpha. Now in the left hand side Q square is common. Let us take that outside. You will have 1 minus of CC by CC plus CS is equal to 2dCO divided by CC times alpha. Now, in the left hand side, it becomes, take the LCM as CC plus CS. So here you will have CC plus CS minus CC is equal to 2dCO divided by CC times alpha. So now this CC and this CC gets cancelled. So you will have Q square is equal to, I will take this to the numerator in the right hand side. So you will have 2dCO by CC. And then you have 1 by alpha in the right hand side. Taking this to the right hand side, it will go to the numerator, CC plus CS. Taking this to the right hand side, it will go to the denominator. So you will have CS. So now our Q will become, Q is a quantity, optimal order quantity or optimal batch quantity, which means it cannot take any negative value. So Q will be square root of 2dCO by CC times alpha. What is alpha? In the beginning itself, we defined alpha as, where is that? 1 minus d by k. So we will substitute that now. One divided by 1 minus d by k times CC plus CS by CS. So that is your economic batch quantity, or we can call it as Q star.